Hello everyone, I'm Yufan from the Johns Hopkins University. Today I'm going to present our work of self-domain adapted network. We're focusing on the domain shift problem. This problem is commonly seen in medical image analysis. If we train a model M on label source domain images XS and test the labels YS, the model can perform badly on target domain images XT when this target data are generated differently from source domain images. Here are two examples. MRI T1 image contrast can vary a lot across scanners and clinical sites. Here are four T1 images from four different hospitals. If we train a model from the T1 image in the first hospital, the model can perform badly on the T1 images from other hospitals. Another example is the retina OCT images from two scanners, Spectralis and Cirrus. A retina segmentation model trained on Spectralis can perform badly on Cirrus data. There are two solutions to alleviate this problem. We can train a more generalizable model with various source domain datasets, or we can use the unsupervised domain adaptation method with unlabeled target domain images XT. We're only focusing on the second methods. The second unsupervised domain adaptation method can be further categorized in two ways. The first is pixel level harmonization, where we translate target image XT to look like source image XS. Methods like histogram matching or cyclogram can be regarded as pixel-level harmonization. The second is to train a model M to learn domain invariant features. We train the model M such that the target features Ft and the source features Fs are not distinguishable by discriminator or classifier. The drawbacks of the current existing unsupervised domain adaptation methods includes requiring fair amount of both source and target image, and the model needs to be retrained for each target domain. So the ideal case and our goal is to find a model that can quickly adapt a single test subject to source domain at inference stage. And here we propose our method called self-domain adapted network, which consists of three parts. The first is the task model. It's a prediction model for segmentation or synthesis, which we use a UNet in our experiments. The second is the autoencoders. It's fully convolutional autoencoders to encode source image access, hidden features 1 to 6, and output YS. So here we use this AEX to autoencode this input image XS, and the features from the same resolution level are concatenated and sent as input to the autoencoders. For the training, we have this offline training the test model and autoencoders on source domain images. We first train this test model T on source image XS and the label S YS using any conventional deep learning training methods. And then we freeze the test model T and train this autoencoders to reconstruct this XS, YS, and features from this trained test model. After that, we introduce our adapters. These adapters are simple convolutions to adapt to a single test target image XT. On the testing stage, we first freeze the weights of the test model and autoencoders which are trained from the source domain, and then we perform online training of the adapters on a single test target domain subject by minimizing this autoencoders reconstruction loss. The core idea is to use those adapters to transform target image and features to get close to source image and feature, which are measured by autoencoder reconstruction loss. However, this method has a major challenge. The gradients from autoencoders reconstruction loss are not always useful to train the adapters to align target and source features. On the left image, the dashed line are our trained classifier, and it performs well on source features, but it fails to classify the domain shifted target feature. If we don't constrain the adapters, we will have this feature mode collapse problem. It's because the target features can collapse to the same cluster, which can be reconstructed well by the autoencoder. To alleviate this problem, we need to constrain the transformations of the adapters. We have a pixel level adapter AX, and we constrain it to a 3-layer 1x1 convolutions, so it can only perform histogram manipulation. Second, We constrain the feature-level adapters A1, A2, A3 to be one-by-one convolutions, which can be represented as a matrix multiplication on the feature space. To avoid feature collapsing, we want to maintain the feature distance before and after transformation. WAI is adapter's convolution kernel, and FA, FB are two feature vector. In order to maintain L2 distance, we need WAI to be orthogonal. So we train the adapters using both autoencoder reconstruction loss and orthogonality loss. Here are the recap of the key points of our method. So our goal is to find a trained model that can quickly adapt a single test subject to source domain at the inference stage. So how to define adapt to source domain? Recall autoencoder for anomaly detection. We think source domain is normal, while target domain with domain shifts are abnormal, and we have large reconstruction error. So when autoencoder has small reconstruction error, we think the target data has been adapted to the source domain. The second key point is how to adapt quickly and use only a single subject. During adaptation, large models like task model are frozen and only the simple adapters are trained. Third, how to avoid target feature mode collapse when training with autoencoder reconstruction loss. We constrain adapters to be simple convolutions and add orthogonality loss to the adapter weights. Fourth, how to make sure the model are still performing the correct prediction after adaptation. The test model is trained on source domain and kept frozen in adaptation, so we can make sure the test model is still performing the prediction. We perform experiments on two image analysis tasks. The first is the OCT layer segmentation from two different scanners, Spectralis and Cirrus. We train the segmentation model on Spectralis and test on Cirrus. The second is the T1 to T2 synthesis from four different hospitals. We train T1 to T2 synthesis model from the JHU dataset and test on the REST HH, IOP, and GH dataset. This is the layer segmentation die scores on the target series scanner. Our method improved the overall die score from 0.749 without adaptation, the NA column, to around 0.8. We also compared to the CycleGAN methods, the CYC column. The CycleGAN is trained with both Spectralis and additional series data, while our method is only using a single series test subject and takes about 30 seconds. We also show results on test data from source domain. Without adaptation should have higher accuracy since the test data is from source domain. If we apply our adaptation method to the source tested data, the results are comparable with no adaptation. Here are the visual results. We can see segmentation errors if not performing any adaptation, and the results are improved with CycleGAN and our methods. Notice that CycleGAN image looks like source Spectralis image, but our adapted image are not improving. That's because we have both pixel level adapter and feature level adapters. So even the pixel level adapter is not adapting the target image to the source image. The intermediate features are adapted to make results better. This is the quantitative results of the T1 to T2 synthesis results. We compare the MSE and SSIM of the synthesized T2 and the real T2. For MSE, the lower the better, while for SSIM, the higher the better. Compared with no adaptation, we achieved better results. We also compared with the CycleGAN, which is trained for each hospital using both source and target data. We achieved the comparable results by using a single test image and additional 30 seconds adapter training time. This is the visualization of the T1 to T2 synthesis. On the left are the source and target real T1 and the T2 images. On the right top are the CycleGAN adapted image and our adapted image using pixel level adapter. The right bottom is the synthesized results. We achieved visually comparable results with CycleGAN while much better than no adaptation. To conclude, we proposed a novel self-domain adaptive network which can quickly adapt to the single test subject at inference stage. The major limitation of the work is that we are only considering minor domain shift that can be solved by relatively simple adapters. Future work will include incorporating the other self-supervised methods and the better autoencoders. Thanks.